Hey guys, this is the last section of chapter 11 we're going to study, and this is talking about arc length of vector valued functions. So we've got a vector valued function, and we're going to kind of zoom in here on a section between k minus first and the kth iteration of t, the different values of t that we're given. So if we kind of zoom in here to kind of show you what's going on, we got the 2 points right there, and this is how x changes, how y changes, and we got the absolute values to indicate that in our picture it's positive for both, but it could have been negative, and the absolute values kind of keep it positive just because we're just talking about how it changed distance wise basically. And then the Pythagorean theorem could be used to approximate that arc length. Okay, it's an approximation of the arc length. This isn't exactly the arc length, but it's an approximation. And then the idea is going to be like Riemann sums, is to shrink the delta x smaller to where this gets closer, and then the approximation's better, and then you get closer and approximation's better, and eventually delta x will go to 0, which will make an infinite number of these little subsections here, just like the Riemann sums. Alright, and anyway, what I've got here, this picture down here, will be explained a little bit more on the next slide. This is because x is a function of the parameter t, and y is also a function of the parameter t. The change in y and the change in x, those values can be written as the change in x divided by the change in t times the change in t. And we'll talk about that in just a second so we can see where this is coming from. This arrow is actually just pointing to the numerator. The numerator is a change in x. The numerator is a change in y. If you think about how we've actually done something similar to this back in Calculus 1, just arc length in general of a function, not of a vector valued function or a parametric function, but just a function, just y equals f of x. We did something similar to this. We made the right triangles, and we came up with, alright, since this is delta x, this is delta y, this is their hypotenuse that's coming from the Pythagorean theorem, and we pulled out the delta x squared, and because that was a square under a square root, we pulled it out as just delta x. And then we notice this change in y or change in x. That's the straight line slope, the approximation of what we're trying to come up here for that curve. At that straight line slope, by the mean value theorem, there is some point in between the two x values here that would have the exact same slope for the derivative that the slope here on the secant line here has. So there's a tangent line slope that's parallel to the secant line slope for some point in there. Alright, and since that is delta y delta x, we can change that and replace it with the derivative. So the derivative squared, that delta x came out. Okay, we're going to do something similar to that, meaning we're going to have something where we have the delta x multiplied by the change to kind of cancel out these and leave us just with that change in y. So this right here, this delta x and delta y, we're going to write them as changes in the parametric function that's given us x by multiplying both sides by the change in t. Okay, if I multiply both sides by the change in t, this would go away, and then I have the approximation for the change in x is equal to that derivative, how x is its own function of t, and that's got its own little curve going on. Okay, remember we're putting the two together to make these points on this curve, but independently x is its own function of t, and so as just like with the previous thing, as t changes from k minus 1 to k, x is changing, and we're getting the same thing that we did in the picture from like the Calculus 1 example. Alright, so anyway, the point is that we can take these delta x's and delta y's and write them as a product of the derivative of the function that's determining the position for x at some value for t within each of these little subintervals times the change in t, okay, and do the same thing for y. So we multiply both sides by delta t for y as well, and we get that delta y is equal to this change in the derivative of the function that's given us the y values at certain t values times the change in t. So these two things can be expressed as derivatives times changes in the derivatives. Okay, and then notice they're going underneath this radical here. Alright, so keeping that in mind, this is what we're doing. Okay, again, this is delta x over delta t, what we just talked about. So that's being replaced into this thing right here where the delta x is. Alright, and then similarly, we're doing the same thing for the change in y. So these things right here are being replaced with those derivative times the change in the differential. Okay, again, it's very similar to when you did the linear approximations in Calculus 1. So, you know, I want to know how the y values changed from you know, this x point to this x point, x2, and I use the tangent. This is, you know, the slope of this thing is f prime at x1, and I use the tangent line approximation. I use this value to come up with, I use the original f of y value, the original x value, and the derivative to approximate this y value. That was where the first time you ever saw this was in Calculus 1, linear approximation. And it's the same concept that we're using here. These tangent lines, and along with the mean value theorem, are giving us a way to use the derivative to approximate the changes in y, or the change in the function. Alright, it's just now that x and y are both functions of a third parameter, or a third variable t. So anyway, that's what's going on here. We're just replacing those changes in x's and changes in y's with those derivatives times the differentials in t right here. Right, and because they're being squared, because of the Pythagorean theorem, they're being squared. So the delta t's in both cases get squared. And then because it's square and it's common to both, we can factor it out just like we did before. It comes out of here, and it leaves us with this. And then we have something that looks very much like a Riemann sum, like we did in Calculus 1. And when we took that Riemann sum of this thing, we ended up with a definite integral to give us arc length. Alright. Exact same concept here. We replace these things, we get this, and then as delta t goes to 0, or the number of these little sub intervals that we're talking about, n goes to infinity, we get a Riemann sum. Okay, and so that's the derivative of the functions that give us x's and y squared. And then we take the square root. So the reality is, when we extend it to 3, there'll be a third, an h prime of t. So the reality is, what happens here when we extend it to 3 dimensions? The derivative of the f, g, and h, if there is a third dimension, when we square those things and take the square root, that's just the same thing as magnitude. So the arc length for the vector value functions, we basically take the derivative of the curve, of the functions that give us the curve, and just find its magnitude. Because remember, you square each one and take the square root, that is magnitude. So we just find the magnitude of the derivative vector, and then integrate that thing from the lower value of t to the upper value of t that they're giving us. Okay, so that's how we find arc length for vector value functions. Derivatives magnitude over the interval that's given. Okay, so this is some examples from your homework just to practice. So this is our trajectory. If we find the derivative, which, basically we're talking about the derivative of, if this is like a position, this is trajectory, and we're talking about speed, or its magnitude of its velocity, which would be speed, right? If this is position, then this would be, the derivative would be velocity, and the absolute value of velocity is speed. Alright, so same thing, we're going to take the derivative of this guy. So 10 cosine 4t, that's going to be 40 sine 4t, and because the derivative of cosine is negative sine, we have a negative right there. Alright, and then comma, same thing, we're going to get a 40 cosine 4t. Alright, and then we find the magnitude of this. So the magnitude of this vector, we're going to get this guy squared, so negative 40 sine 4t squared, right, we should square that, plus 40 squared cosine squared 4t. Right, and then the square root of all that stuff. Alright, 40 squared and 40 squared is common in both. Negative 40 and positive 40 are the same thing. And because it's squared, we can pull it out of the radical and it'll come out as a 40. And then if you look at what's underneath there, you got a sine squared 4t plus cosine squared 4t, which is equal to 1. And now we integrate that. So 40 from 0 to pi dt is just going to be 40 pi. Alright, you get 40t, pi goes in, 0 goes in, so you end up with 40 pi. Alright, that's how much that thing travels. Alright, and then the same thing here. Let me grab this into another page. We want to approximate the length of this curve. So I got a r prime. I gotta find its derivative. So the 3 comes down, I'd have a 2t squared. I have a 22t, and a derivative of a constant is 0. Alright, and then the magnitude, it's going to be the square root of 4t to the 4th plus 22t squared. Alright, then I'm just going to simplify. I got a 4 that can come out, a t squared that can come out. So that'll be a 2t. Okay, if I pull this 4 out of here and this common t squared out. So I'm pulling it out of the radical as well, so that's why it's coming out as a 2t. Alright, then I'm left with a t squared from the first piece. Alright, and then 484 divided by 4 is going to be 121 dt. Okay, and now this is our integrand. And then we're going to integrate that from 0 to 4. Alright, so there's our integrand. I notice here t squared plus 121 under the radical, 2t outside of the radical. So that's u substitution for the technique. So t squared plus 121 is our u. Du will then be 2t dt. So we have everything we need to do this integration. There's the 2t dt. This is now square root of u, or u to the 1/2. So this becomes u to the 1/2 du. Oops, that's, yeah. And then we're going to substitute in here. So these, again, this is in terms of t. So these limits integrations are t's. Alright, so since u equals t squared plus 121, that means 0 squared plus 121, which is 121. And then the upper limit is 4 squared, which is 16. 16 plus 121 is 137. Alright, and then u squared, the integral of that would be u to the 3 halves over 3 halves, or 2/3 if we flip it. And then we're plugging in 137 and 121. And there's our integral that we'll end up using. So 2/3. Alright, so plugging everything in, 2/3 times this goes in 137 to the 3 halves. This goes in 121 to the 3 halves power. So there's our interval, 181.7 roughly. Alright, and then back to the problem for our units where, it doesn't say. So that's just, it's not feet or inches or miles, it's just ones. So 181.7 roughly is our interval. You can use technology, you can use Wolfram for this thing. You could have just treated these as x's and put it into your calculator, like press the math, oops, sorry, not on the screen. So what I did is I pressed the math button on this, and then you can do fn int. You could have plugged in your function right here, 2t, you'd have to use x, because it's just what's on the faceplate, 2x times the square root of x squared plus 121, right? And then tell it comma, you have to tell it the variable, so the variable's t, but we use x again for this, so x, and then tell it your limits integration, so from 0 to 4, and then it does a numeric integration. It's going to give you an approximation. Anyway, okay, it gives us that same thing that we got there. Okay, so you can use software if it tells you in the problem like this to round. Alright, then you can just use software to do that integration for you once you get it set up.